Sejam muito bem-vindos. Meu nome é Robson Rodrigues, sou repórter e editor aqui do canal OLHAR SIDERAL. Estamos aguardando a transmissão da NASA para a teleconferência que tratará dos assuntos sobre as novidades e as descobertas realizadas pela sonda OSIRIS-REx. A OSIRIS-REx passou mais de 2 anos perto do asteroide Bennu, que tem 500 metros de largura, e durante esse tempo a espaçonave coletou informações sobre o tamanho, forma, massa e composição de Bennu, enquanto monitorava seu giro e trajetória orbital. Antes de deixar o objeto próximo à Terra em 10 de maio de 2021, a espaçonave coletou as amostras de rocha e poeira da superfície do asteroide. OSIRIS-REx retornará a amostra para a Terra em 24 de setembro de 2023, para os estudos científicos adicionais. Se você é novo aqui no canal, seja bem-vindo, muito obrigado pela sua presença. Aproveita para deixar o seu like, se inscrever e comentar também, isso é muito importante. O YouTube considera isso como relevância e disponibiliza também esse conteúdo para mais pessoas. Visite também nossas redes sociais, no Facebook, OLHAR SIDERAL, no YouTube, também OLHAR SIDERAL. Quero agradecer a presença do meu amigo Cairo. Cairo, seja bem-vindo, nosso moderador de hoje aqui no canal. É um prazer ter você de volta aqui à nossa casa. É um grande orgulho a sua presença. E para você também que é novo aqui, que está assistindo, se inscreva no canal, aproveite e comente. Os participantes de hoje do briefing serão Dani Laureta, coprodutor do estudo e pesquisador principal do OSIRIS-REx na Universidade do Arizona, em Tucson; David Farnokutia, autor do estudo e cientista do Centro de Estudos de Objetos Próximos à Terra no Laboratório de Propulsão a Jato da NASA, no sul da Califórnia; Jason Working, cientista do projeto OSIRIS-REx, no Goddard Space Flight Center da NASA, em Greenbelt, Maryland; e Lindley Johnson, oficial de defesa planetária do Escritório de Coordenação de Defesa Planetária da NASA, na sede da NASA em Washington. Estamos aguardando o sinal em definitivo. Enquanto isso, aproveite para deixar o seu like, comentar, compartilhar com os amigos. Isso ajuda ao canal ter relevância.
Welcome and thank you for standing by. At this time, all participants are in a listen-only mode. During the Q&A session, if you'd like to ask a question, you may press star 1 on your phone. Today's call is being recorded. If you have any objections, you may disconnect at this time. And now I'll turn the call over to Ms. Ronnie Grand. You may begin.
Hi, I'm Ronna Grant, Public Affairs Officer at NASA Goddard Space Flight Center, Greenbelt, Maryland. Welcome to today's media telecon to discuss asteroid Bennu and planetary defense. For those watching via Ustream at nasa.gov/live, please note there will be a 30-second delay in the streaming to the actual telecon. Graphics related to the telecon are on our Scientific Visualization Studios site. The link to the SPS will be shown on nasa.gov live, or another way to get there is you could do a keyword search for NASA Scientific Visualization Studio. Once you're on their site, you can go to the search box and type 13906, and that will take you to the right page. Again, keyword search NASA Scientific Visualization Studio, and type the number 13906. And just a note, the NASA Scientific Visualization Studio has a catalog of animations and visualizations and videos featuring NASA science research and mission. Okay, today we have 4 panelists joining us. Each panelist will provide brief remarks. Then we move to question and answer session, accepting questions from media that dialed into the phone bridge and those that submit questions via Twitter using the hashtag AskNASA. This media telecon will be limited to 1 hour. NASA's first mission to collect a sample from an asteroid, the Origin Spectral Interpretation Resource Identification Security-Regolith Explorer, or OSIRIS-REx, is on its way back to Earth with a bounty of material, holding a time capsule with clues about the formation of the solar system. However, OSIRIS-REx has another important mission, and that's security. Asteroid Bennu is one of the most hazardous asteroids to Earth. For 2 years, OSIRIS-REx orbited Bennu, collecting information about the forces that will affect the asteroid's path. Today, the journal Icarus will release the results of that study. Our panelists will talk about the science results and its implication for other hazardous asteroids. The panelists are Dante Loretta, study co-author and OSIRIS-REx principal investigator at the University of Arizona in Tucson; Davide Farnocchia, study lead author and scientist with the Center for Near-Earth Object Studies at NASA's Jet Propulsion Laboratory in Southern California; Jason Dworkin, OSIRIS-REx project scientist at NASA Goddard Space Flight Center in Greenbelt, Maryland; and Lindley Johnson, Planetary Defense Officer at NASA's Planetary Defense Coordination Office at NASA headquarters in Washington, D.C. Now I'd like to hand it over to Dante.
Thank you, Ronnie. Can everybody hear me okay? Yes? Okay, let's get started. I'm going to start out with a status update for the OSIRIS-REx mission. And if you look at my first graphic, it's an orbit diagram showing the positions of OSIRIS-REx, asteroid Bennu, and the Earth today, August 11th, 2021. And the mission is in great shape right now. We have completed our primary encounter with the asteroid, and we collected samples successfully on October 20th, 2020. We departed from the asteroid on May 10th of 2021, and the spacecraft's basically on cruise control right now. That departure maneuver, which required firing the spacecraft's main engines, basically set us up on a ballistic trajectory that will intersect the Earth on September 24th, 2023. And OSIRIS-REx is driven by the primary objective to obtain and return a sample from asteroid Bennu to Earth for scientific study in our laboratories. And the orbital diagram shows you why Bennu was such a great target for this mission. It has an orbit that is very Earth-like. It actually crosses the Earth's orbit, as you can see there on the point labeled sample return. That's what we call the ascending node of Bennu's orbit. It is slightly inclined, so before it reaches that point in September 24th, 2023, it's a little bit below the orbital plane of the Earth. And then as it crosses that point in time, it actually crosses right over the orbit of the Earth and then goes a little bit above it. So it's about 6-degree inclination between Bennu's orbital plane and the Earth's orbital plane, which is very low. And that kind of orbit is ideal for a sample return mission. We needed to find an asteroid where we could launch a spacecraft off the surface of the Earth, spend a substantial amount of time around the asteroid to survey it, identify the best site on the surface to collect a sample, and then bring that material back to Earth. So kind of as a consequence of the primary mission objective of sample return, we ended up selecting an asteroid that is also categorized as potentially hazardous, which means it has a non-negligible probability of impacting the Earth at some point in the future. And so we incorporated that into our mission planning, and particularly it became a primary mission objective to understand the orbital trajectory of asteroid Bennu well into the future and update the impact hazard assessment. We spent 2 years studying this asteroid, and if you look at graphic element number 2, which is the web around asteroid Bennu, you can see that the trajectory of the spacecraft was really amazing. I compare it to a hummingbird. We're able to go into orbit. We were able to leave orbit. We could get to a variety of imaging angles so that the sunlight was either casting long shadows or casting no shadows, depending on the scientific measurement that we were making. And in addition to all of the great mapping and other mineralogical information that we acquired of the asteroid, OSIRIS-REx was operating as a demonstration of what they call in the planetary defense community a transponder mission. We're able to use the position of the spacecraft relative to the Earth and the position of the asteroid relative to the spacecraft to do the amazing study that we're presenting to you today. So we're going to hear from study lead author Davide Farnocchia about the fantastic results of what him and the rest of the team were able to accomplish. And it's really an amazing demonstration of the incredible precision that we can obtain with this kind of mission to a near-Earth asteroid about its orbital parameters and where it's going to be in the future. And then you'll hear from Davide about where the uncertainties arise from still. And then because we are a sample return mission, we are going to bring that material back. As you'll hear later, one of the important parameters that controls the orbital dynamics is how the asteroid absorbs solar radiation and re-emits that energy back into space as heat. That provides a thrust which changes the orbital velocity of the asteroid and is a contributing factor to understanding its orbital evolution. So our study isn't complete because the sample is going to give us more information about the fundamental physics that are driving the orbital characteristics that we're going to present to you today. So another prime objective of the mission, and we don't codify it in the acronym or talk about it, specifically, but it is about enabling the next generation of scientists and engineers to enable these kinds of fantastic missions of scientific exploration to continue into the future. And Davide is a great example of our success on this mission in doing that. So with that, I want to hand it over to Davide Farnocchia, who is the lead author of the study, to tell you the details of what we have learned about the orbit of asteroid Bennu.
And Davide, I'm going to interrupt you just real quick, just to remind people following along online and on the phone that we do have, you can follow along with the graphics and the speakers on the Scientific Visualization Studio site. There is a link in nasa.gov/live, which is sbs.gsfc.nasa.gov/13906. All right, go ahead, Davide.
Thank you. Yeah, I still remember actually when I first learned about the OSIRIS-REx mission, it was actually the day the mission got selected. It was 2011, and at the time I was a PhD student at the University of Pisa back in Italy, and I was in the process of getting an appointment to work for NASA's Jet Propulsion Laboratory. One morning I entered my PhD advisor's office, and he's going through his email, and suddenly at some point he turns to me and says, Davide, do you want to know the latest? The OSIRIS-REx mission has just been selected. Now we know what you're going to be working on once you go to work for JPL, Jet Propulsion Laboratory. And sure enough, I've been very busy and very happy working on this amazing mission for several years now. Before I get into the details about the paper, I think it makes sense to provide some background on Bennu. As Dante mentioned, Bennu is one of the potentially hazardous asteroids, which means it's fairly sizable. It's about ½ kilometer in diameter, and its orbit has the potential of bringing it close to the Earth. These are the objects that we really pay a lot of attention to at the Center for Near-Earth Object Studies. We want to ensure these objects get properly tracked, We want to get data for these objects so that we can use the data to precisely compute their trajectory, predict their future motion, and assess whether or not there is a possibility of an impact. And for Bennu, the asteroid community at large, has done an amazing job. Bennu was discovered in 1999, and since then it's been extensively tracked using both optical and radar telescopes. The amount of data collected, even before the OSIRIS-REx mission, gave us one of the best known orbits in the entire asteroid catalog. The orbit was so well known that we could predict its exact motion all the way to 2135. That's more than 100 years into the future. What happens in 2135? Well, in September 2135, Bennu is going to come close to the Earth. And even though there is no possibility whatsoever of an impact during that encounter, Bennu is going to be fairly close to the Earth. The distance is going to be about half the distance between the Earth and the Moon. And when you come that close to the Earth, the gravity of the Earth is going to change your trajectory in a significant way. And in order to know the trajectory after the encounter, you really need to know the position of Bennu right before the encounter so that you can model how the gravity is going to perturb the motion of Bennu. And in particular, we have to deal with the so-called gravitational keyholes. Keyholes are narrow locations in space at the time of the 2135 encounter. If Bennu were to pass through one of those keyholes, then the gravity of the Earth would tweak the motion of Bennu by just the right amount to put it on a collision trajectory at a later date in the 22nd century. So we really want to avoid those keyholes. However, there is a problem that in order to model and predict the position of Bennu in 2135, we need to account for a subtle non-gravitational perturbation called Yarkovsky effect. The Yarkovsky effect is due to sunlight reaching the asteroid and warming up its day side. As the asteroid is rotating, the night side cools down and the heat gets released. And that causes a gentle push on the asteroid. And that's a very small push. I'll make an analogy. The Yarkovsky effect acting on Bennu is equivalent to the weight of 3 grapes. Think about that, just 3 grapes. And that's what's really driving the motion of Bennu into the future, because this acceleration, it's persistent, its effect builds up over time, and it becomes very significant by the time we get to 2135. So what's the problem with it? Well, the Yarkovsky effect really depends on the specific properties of the asteroid you're working on. In particular, you need to know the asteroid size, mass, shape, rotation state, surface, and thermal properties. And those are information that are really hard to collect from the ground. It's really hard to measure this kind of information from the ground. And that's where the OSIRIS-REx comes in, because the spacecraft went to Bennu, it stayed in orbit for about 2 years, collected all the data we needed in order to quantify these physical properties. And that gave us all the ingredients we needed to compute the Yarkovsky acceleration and account for that as we modeled the future motion of Bennu. So that's really one of the major contributions from the OSIRIS-REx mission when it comes to modeling the trajectory of asteroid Bennu. The second component, as Dante mentioned, is the fact that by tracking the spacecraft over 2 years of proximity operations, we obtained fantastic positional constraints on the position of Bennu. We measured the distance between the Earth and Bennu, which at times was as large as the distance between the Earth and the Sun, with a precision of 2 meters. That's the height of a basketball player. That's how well we can constrain the position of Bennu. But of course, with great responsibility comes with great power comes great responsibility. Well, with great powerful data come great challenges. We really needed to step up to the challenge and model the trajectory of Bennu to a level that was never tried before for any asteroid. And so beyond the gravity from the sun, the planets, the already mentioned Yarkovsky effect, we also have to account for other solar radiation forces, Einstein's relativity, and the gravitational pull coming from hundreds of other asteroids in the solar system. We also had to check other small terms that we thought were not relevant, but at this level of precision, we really needed to go down, check the numbers, and ensure that that was the case. And I'll mention 2 examples that I find particularly interesting. The first one is related to one of the most interesting and surprising scientific discoveries from the mission, which is the fact that Bennu ejected particles. And that was extremely valuable from a scientific standpoint. But there is a question, is that affecting the motion of Bennu? Well, we went through the numbers, quantified how much that could change the motion of Bennu, and determined that was not significant. The other obvious example is the interaction between the OSIRIS-REx spacecraft and Bennu, especially during the sample collection sequence. As the spacecraft went down to the surface and collected the sample, it touched the asteroid. Is that enough to perturb the motion of Bennu? Well, again, we spent our time, computed, the size of this effect, and established that that was not affecting the motion of Bennu in any significant way. So we did our homework and made sure that we didn't forget anything. So after all this fancy modeling, what's the result of this study? Well, we have a much better knowledge of the trajectory of Bennu. And that's impressive because, as I mentioned before, even before the OSIRIS-REx mission, we already had one of the best known orbits in the entire asteroid catalog. Well, thanks to the OSIRIS-REx mission, we improved that knowledge by a factor of 20. We have a knowledge of the position of Bennu in 2035 that is better by a factor of 20 than what it was before. And that allows us to rule out many of the possible keyholes that were out there. Just to quantify this, we had about 26 keyholes greater than 1 kilometer that were a possibility before the OSIRIS-REx mission. Now we only have 2 of those keyholes greater than 1 kilometer that we need to consider. So this improved knowledge confirmed that Bennu is going to miss many of those keyholes, even though a few of them remain a possibility. The benefit is that now we have a much better knowledge of what the pathways to impact can be, and the most significant one would be to an impact in 2182. But we should keep in mind that the impact probability overall is really small. In fact, the overall impact probability is 0.06%, which put another way means that there is a 99.94% probability that Bennu is not on an impact trajectory. So there is no particular reason for concern. We know that Bennu is still a potentially hazardous asteroid, but the probability is small, and we have time to keep tracking the asteroid and eventually come to a final answer on whether Bennu is going to pass through one of these keyholes or not. More in general, and to provide some more perspective, we should remember that the risk carried by Bennu as an individual asteroid is actually smaller than the risk coming from the undiscovered population of objects of a similar size. And that's why NASA is making a big effort to discover more than 90% of the near-Earth objects greater than 140 meters in size. And I think Linda is going to mention something about that. So with this, I'll hand it over to Jason for some update on the mission.
Thank you. So in the first graphic, we'll remind you that the OSIRIS-REx mission last October collected an enormous amount of sample, so much so that it overflows the sample collector, but was successfully and safely stored within the sample collection device and is on its way back to Earth to land in Utah Test and Training Range, September 24th, 2023. So mark your calendars. And that this sample will help improve our understanding of the composition of the asteroid. By looking at the thermal physics that leads the Yarkovsky effect at the microscale, we can better understand the causes of these effects, the causes of the thermal inertia that we observed on the asteroid that has led to the Yarkovsky effect, as well as studying the strength, density, cohesion, and elastic properties of the regolith that we bring back. We can study that in great detail, such that if it becomes necessary in 2136 to develop a strategy to deflect Bennu, we'll have the information both based on our in situ results by contacting the asteroid with a touch and go maneuver, as well as the properties of this material. And so in the next graphic is to remind you that just like the samples from the Apollo mission over 50 years ago, material will be archived. 75% of the sample that we have collected from Bennu will be archived for future generations. And we can study the sample properties and, like I said, the thermal physics properties and the chemical properties and the strength, density, and cohesion now, as well as future generations can look at these if they need to come up with strategies on how to interact with Bennu if a diversion is necessary. In addition, of course, to the massive scientific information of the other aspects of OSIRIS-REx. Likewise, we are fortunate that that JAXA, the Japanese Space Agency, Hayabusa 2 mission has returned samples from asteroid Ryugu. And we can compare the samples from Ryugu with the samples from Bennu to understand how observations of Bennu can perhaps better explain the behaviors of other asteroids in general. And I'll turn this over to Lindley Johnson, Planetary Defense Officer, who can talk more about how we can understand the whole asteroid population from Bennu. Thank you.
Thank you, Jason. Thanks, Jason. OSIRIS-REx is a planetary science mission and it's not part of our planetary defense portfolio. But planetary science on solar system small bodies, the asteroids and comets, this goes hand in glove with planetary defense. Closer study of asteroids tells us what we need to know about them to better discover, characterize, and mitigate any potential impact hazard to Earth. Planetary defense, as I like to say, is applied planetary science. In fact, Bennu was originally found by one of our early NEO survey projects, the linear project that conducted by MIT Lincoln Labs. The OSIRIS-REx mission has provided exquisitely precise data on Bennu's position and motion through space to a level never captured before on any asteroid. Not only does this allow us to better understand Bennu's future path, and if it could ever be an impact threat to Earth, but also allows us to test and improve the orbital modeling techniques that we can use on all near-Earth asteroids, as Davide talked to you about. OSIRIS-REx and other missions to asteroids also provide up-close and detailed inspection of the size and structure of these objects that we can compare with observations that we have taken from Earth using telescopes on Earth, and better understand if the fidelity of these remote observations that we take from Earth and how they apply to the nature of the other objects. And OSIRIS-REx and Hayabusa have and will be bringing samples back to Earth, which help us to better understand their composition to aid in the design of techniques and technologies that might be used to mitigate a potential asteroid impact threat to Earth in the future. This is the most detailed information we could ever hope to get for the characterization segment of our planetary defense portfolio, which you see depicted in one of the slides, the five sectors of planetary defense. Therefore, OSIRIS-REx mission is and has been a pathfinder for capabilities to study any newly discovered hazardous asteroids. And what has been learned can be applied to future missions more specifically designed for reconnaissance of hazardous asteroids. We now know a lot about Bennu, but what about what else is out there? Our attention for planetary defense can now turn back to finding more of the potentially hazardous population, which is exactly what we're doing with the recently approved Near-Earth Object Survey mission, which is another mission that will be led by a team at the University of Arizona. Now that we know this much about Bennu, what could we do to divert a similar asteroid if it were on a hazardous trajectory? We are also getting ready to test one technique for mitigating hazardous asteroids called the kinetic impactor. This is our very next mission for planetary defense. It's now in preparation at the Applied Physics Lab to launch in late November of this year. We are sending it to an asteroid called Didymos. It looks very much like Bennu, but Didymos also has a smaller moon orbiting it called Dimorphos. Hence, the mission is called the Double Asteroid Redirection Test. And the spacecraft will impact itself into the moon Dimorphos to redirect its orbit around the primary Didymos to test the effectiveness of this kinetic impactor technique should we ever need to redirect a truly hazardous asteroid. With that, back to you, Ronnie.
Thank you, Lindley. Right now, we're going to roll into the question and answer session. We have several reporters on the telephone bridge today. We'll need to limit everyone to one question and one follow-up. Once everyone has had a chance to ask a question, and if time permits, we'll start from the beginning again. Our operator should identify you, but if not, please identify yourself, your media affiliation, and then direct your question to a specific panelist if possible. For those dialing in, push the *1 keys on your telephone to be placed into the queue. To use Twitter, send your questions to #AskNASA. Operator, let's begin.
Okay, our first question in the queue is from Marcia Dunn with AP. Your line is now open.
Hi, thank you for Dr. Faranokia, I believe. It looks like the odds are greater now that we could take a hit from Bennu, even though it's still slight. We went from 1 in 2,700 through 2,200 to 1 in 1,750 through the year 2,300. I mean, I guess that's the bad news in all this. Is that how you see this? Do you see how much more likely, statistics aside, do you see the threat from Bennu at this point in the next few hundred years? Thanks. Hello? I hope you heard my question.
Yeah, I heard it.
Oh, great.
Hello. Can you hear me now?
Yes.
Can you hear me now? Okay.
Yeah.
Okay. So, yeah, you're technically right that the impact probability went up just a little bit, but it's not a significant change. The impact probability is pretty much the same, and we actually now have a much better knowledge of the Bennu trajectory, and we can better constrain what the possible pathways to impact are. So I think that overall the situation has improved, and I'm not any more concerned about Bennu than I was before. The impact probability remains really small, and so no particular concern. We're going to track Bennu and have a final answer at some point, but we shouldn't be worried about it too much.
Okay, operator, next question.
Next question is from Kenneth Chang with New York Times. Your line is now open.
Hi, thank you. So just following up on the odds. So the odds are slightly higher, but there's fewer keyholes. So presumably that means that the chance of going through the remaining keyholes is considerably higher than what you had before?
Well, so what happens is that the probability of going through, let's say, the 2182 keyholes are now much higher than they were before. But overall, you were able to rule out many of the possible keyholes that you had before. So it's essentially, the uncertainty shrinks, and whatever remains inside the probability is going to have higher chances than it did before. But the benefit is that you get to rule out many of the possibilities, and that's key.
Okay. And just a quick follow-up. Are there any years between 2200 and 2300 where there are significant chances of impact?
Well, the paper gives a list of all the possible, impact chances. And as I said, 2182 is the most significant one. There is other dates like 2187, 2192, 2194. There is some possible impacts, but as I said, the most significant one is 2182, and the others have a much smaller impact probability.
Thank you.
Next question is from Alexandra Witze with Nature magazine. Your line is now open.
Hi, thanks for taking my question. This is also for Davide. Can you talk a little bit more about how measurements of the spacecraft's position allowed you specifically to determine the Earth-Bennu distance, and also whether there were any observations taken sort of the physical properties of the asteroid itself that played any role in this new and revised impact assessment?
Yes. Okay. So what happens is that whenever you send a mission in deep space, you're going to track the spacecraft using stations with the deep space network, and you're going to send radiometric signal to the spacecraft. One of the most valuable pieces of information is this so-called range measurement, that essentially you measure how much time it takes to go to the spacecraft and comes back. And that's usually known to within 2 meters. which is of the order, the order of nanoseconds, just to get an idea, 10 to the minus 9 seconds. So, and that gave us a very good knowledge of the position of the spacecraft relative to the Earth. Then as the spacecraft is in orbit about Bennu, you collect optical navigation data, so you essentially see where Bennu is and where the features on the surface are. You also get Doppler measurements, and that gives you a very good knowledge of where the spacecraft is relative to the asteroid, and that's known to about 1 meter. So if you combine these two pieces of information, you can work out the distance between the Earth and Bennu. And as far as the data collected, I would say probably the most important piece of information was measuring precisely the mass and also getting the temperature profile from thermal measurements on the surface. Those were key really to get the right modeling for the Yarkovsky effect.
Thanks.
Next question is from Nell Greenfield-Boyce with NPR. Your line is now open.
Thanks for this. So I understand that, you know, all these things that went into this refined trajectory. Am I correct in understanding that we basically won't get any more useful information between now and 2135? Like, at that point, will you all be able to know, you know, what the, you know, if it does indeed seem like it's going to hit the Earth when it returns?
Okay, so I think I'll take this one as well. Well, in 2135, you'll know for sure, but we're going to keep observing Bennu even before that. In particular, there is a very good opportunity in 2137. Bennu is going to come close to the Earth, not as close as in 2135, but close enough to collect radar data. And at the time, we're just going to see how much that those observations are going to improve our knowledge on the trajectory, and chances are that the uncertainty would shrink a little further. But yeah, we're going to keep tracking Bennu, and chances are we're going to know before 2135 at some point, even though it's not clear yet at what point we will be able to get a final answer.
Next question is from George Dvorsky with Gizmodo. Your line is now open.
So I guess my question can piggyback off the last one. And I guess Dr. Dworkin could perhaps answer this one. Once we get our hands on these sample materials and we can run these thermal physical analyses and kind of better understand the composition of the asteroid, couldn't that conceivably change the outlook for 2135, or would those differences perhaps be too trivial to change these kinds of calculations that were presented in the new paper? Thanks very much.
My understanding of this, I'm actually an organic chemist, so I can't speak in detail about the thermophysical measurements. But my understanding is that these are more understanding the reasons that we see the behavior that Davide has already observed and published, not necessarily refining that value. Let me pass it over to Davide or Dante, who might have a bit more complete answer than I can give you.
Yeah, for OSIRIS-REx, this is Dante responding. So the Yarkovsky investigation, from my perspective as the principal investigator, has two components to it. It has what we're talking about today, which is this exquisite modeling of all of the forces that contribute to the orbital solution, allowing us to make the predictions going into the future. And as we see, one of the largest contributors besides gravity is this Yarkovsky effect. And so we really want to understand the physics of that process. So right now we have a very empirical solution. We've basically measured the heat flux that's been coming off the surface of the asteroid as it rotates and as it changes its distance from the sun. If you refer back to the orbit diagram that I showed, and Davide also had an orbit diagram, you see that it actually is sometimes inside the orbit of the Earth. It gets as close as 0.89 astronomical units, where 1 astronomical unit is the average distance between the Earth and the sun, and it gets out as far as 1.35. So you're dealing with a wide variety of solar inputs to the sun, and then we really want to understand how that material responds. Where we may see some interesting inputs to the orbital solution is if the material properties change as a function of their exposure or their solar insolation. We have the current state of thermal emission from the asteroid, and by understanding the detailed thermophysical properties of the sample, we'll be able to understand you think those thermal properties remained constant throughout Bennu's entire lifetime, or are they subject to changes as they go through a process called space weathering, which deals with impacts that could change the nature of the surface, expose fresh material, also cosmic rays, high energy photons from the sun and from other extrastellar sources. So it really will build up the fundamental understanding of the physics that give rise to one of the most important parameters that drives the uncertainty on the orbital solutions that Davide has come up with.
Next question is from Camille Carlot with Sky and Telescope magazine. Your line is now open.
Hi. I had two questions. One, could you explain more why keyholes exist? And also, will you be sending OSIRIS-REx to another asteroid after you drop the sample? And if so, could that also contribute to this conversation about another potentially hazardous asteroid and the chances of getting hit by that?
Well, I'll take...
Dante, let me take the second one first, Davide, and I'll hand it over to you for the keyholes, just to get ahead of that. So right now, the primary mission of OSIRIS-REx is to deliver those samples back to Earth, and that is on plan for September 24th, 2023. We do have the opportunity to propose to NASA an idea for an extended mission concept. That's a normal process that NASA goes through for a lot of the missions as they're approaching the end of their primary phase. There's always looking. We have this fantastic spacecraft with a lot of measurement instruments that are very capable on it still, and we have looked at where else could the spacecraft go into the future. We are going to be submitting our concept to the agency in early 2022, allowing them to make a decision on whether they want to support the concept for an extended mission.
Yeah, and about the keyholes, essentially when you have a close encounter with the planet, in this case the Earth, that really affects the motion of the asteroid and can inject the asteroid on a variety of different trajectories depending exactly on where you are right before the encounter. And some of the positions before the encounter are actually perturbed in the right way by the planet's gravity to put you on an impact trajectory. And so if you identify the set of those positions that lead to a future impact, that's what we call keyhole, and that's what you want to miss to avoid the impact at a later date.
Okay.
Next question is from Megan Bartels with space.com. Your line is now open.
Hi there. Thanks so much for taking my call. I wanted to ask about really digging into that data. You had 2.5 years at Bennu proper, and I'm wondering if you needed literally all that data to refine the trajectory this much, or if a shorter visit or a flyby mission could also have given you the extra details you needed to make these estimates. Thanks so much.
Well, it's always a trade-off. In general, you need to be in orbit in order to constrain the position of the spacecraft relative to the asteroid in such a way that we can use tracking to the spacecraft to constrain the position of the asteroid. And the longer you stay, the longer the constraint becomes, the stronger the constraint becomes on the trajectory. So 2 years was a very good amount. You could have done with a little less, but the amount of information would have been, not as significant. So if you had done 1 year, you would have lost some sizable amount of information. So the longer you stay, the better. But of course, there is other constraints, such as returning the sample back to Earth.
Mm-hmm. Great, thanks.
Next question is from Michael Grishko with National Geographic. Your line is now open.
Hi, thank you so much for doing this. I have a question for Davide related to kind of the lingering sources of uncertainty. I mean, you all have gone through an extraordinary effort to measure Bennu's current position. What are the single biggest sources of uncertainty in the modeling moving forward, including things like gravitational perturbations from other solar system bodies?
Yeah, I'd say right now the biggest source of uncertainty would be related to the mass of all the other asteroids that we are including in the model. And we should really be sending missions to all of them so that we can measure their mass and know exactly what their effect is. In our study, what we did is to use the best known estimate for that mass, but also to account for the uncertainty in that mass, and folded that into the uncertainty of the trajectory of Bennu. So getting the mass of the asteroids in the solar system would be the next major step in improving this trajectory.
A quick follow-up to that. In a few years' time, NASA will be launching the NEO Surveyor. It's an infrared space telescope that's especially well suited to measuring the sizes of asteroids. How useful will those data be in at least constraining those asteroid sizes and, helping estimate mass?
Well, for most of these objects that we are including as perturbers, the motion of Bennu, we already have some decent guess of the size. Of course, any surveyor might give us more data. We're going to improve that. We still have uncertainty on the bulk density of these objects, and that's going to affect the uncertainty in the mass. So the size and the density are the two sources of uncertainty for a mass. The size can be well constrained using infrared data. The density remains uncertain, even though you can get spectra, you can get an idea of colors to kind of constrain the taxonomic type and have a good guess of what the density could be.
Gotcha. Thank you.
This is Dante. I just want to add a comment onto that because it was astonishing to me that, first of all, Davide and the team members that were working on this included 343 objects in the solar system that could potentially perturb Bennu's orbit through gravitational interactions. And we got to the point where, because, I would ask, what else can we do with the OSIRIS-REx spacecraft to improve the solution? And they said there's absolutely nothing you can do because the uncertainty lies outside now of Bennu in terms of how the mass is distributed across the solar system. And that just struck me as really profound. We have done everything we can specific to Bennu, and now the uncertainty resides with these other objects that are orbiting around the sun.
And just to clarify, the 343 objects, is that total or is that just in the asteroid belt?
Well, no, it's not just the asteroid belt, even though the vast majority of them are in the asteroid belts. But we also tried to see what happens if you add trans-Neptunian objects that are further out, and we proved that they didn't affect the motion of Bennu in any significant way. So 343 are plenty for modeling the trajectory of Bennu, but we could improve that even further if we had a better knowledge of their masses.
Gotcha. Thank you.
Hi, this is Ronnie Grand. Just reminding folks, we've pretty much got through the first queue of questions. If any reporters have more questions, please hit *1 and join the queue. Operator, take the next question, please.
Okay, next question is from Ken Kramer with Space Up Close. Your line is now open.
Hi, thank you for doing this. My question, I'm not sure, maybe this is for Lindley. I'm wondering how close would this object have to come to Earth to actually cause great concern, besides a direct impact? If I understood you right, you said the distance will be half the Earth-Moon distance. So, again, how close would it have to be to cause concern?
Well, we are monitoring Bennu and all other near-Earth asteroids and comets that we find to determine how close they do come to Earth. Once we have good orbits on them, and that shows that it's just going to be a close approach and not potential for an impact, then they're not of concern anymore. We understand where they are and where they're going. Although we will continue to monitor them, they are not of concern, but we are still looking for what we don't know out there, the objects that haven't been found yet, to determine what their orbits and trajectories are, to find out if any has the potential to impact the Earth. And once we find those that have more significant probabilities, on the order of, say, 1% probability of impacting the Earth, then that's a concern. Then that's when we really get concerned and start talking about what can we do about it.
All right, thank you.
Next question is from John Kelvey with inverse.com. Your line is now open.
Yeah, hi. Thank you all very much for doing this. I'm curious. I understand still very low probability of an impact from Bennu, but I'm wondering if anything else we've learned from these studies thus far tells us anything about our ability to head off an impact if the thinnest of probabilities were to come about. And relatedly, you're still the kinetic impactor study hasn't been done yet, but I'm wondering if there's anything that hints that might be something that could work for Bennu. Do we know enough yet to know what our odds would be of deflecting Bennu if the worst possible and least likely outcome would come about?
Lindley, do you want to take that, or should I go?
I'll try it, and you can certainly add. It kind of broke up there. I'm not sure I got all of the question, but understanding the physical properties of near-Earth asteroids like Bennu, being able to compare them to other observations that we take to help us understand more what the overall population looks like is always a benefit to our looking at what various techniques can be used to deflect them. Of course, the biggest factor in our being able to deflect an object is how far in advance we find them before a potential impact. That's really the most important thing. You've got to find them first before you can do anything, and the further out in time that you find them, the better our chances are, and the more options that we have for doing a deflection. So with Bennu, we know about it, almost 2 centuries before it could pose an impact threat, and that gives us a great amount of time to develop any mitigation technique that might be used against it. And in fact, we're looking at technology 100 years from now, when Bennu does make this close pass by Earth. Hopefully, we'll be much more capable than what we have today. So we don't know what might be used against Bennu because it's 100 years in the future before we have to worry about it. Go ahead, Davide, do you have something to add?
Yeah, the only thing you might want to add is that, let's say that the 2182 impact becomes, a real possibility. You're going to find out in 2135. That's almost 50 years of time to deal with it. That's plenty.
Yeah, this is Jason. If I could also jump in, I'll mention that from our interactions with Bennu, we know that it's a rubble pile asteroid with interior void spaces. When we contacted Bennu, we observed the plumes of regolith being thrown up from the contact. And when we study the samples in the laboratory up close, we'll understand the physical behavior of the particles, such that if technologies are developed that involve impacting or touching the asteroid, we'll know how the surface will respond to those technologies.
Next question is from Nell Greenfield-Boyce with NPR. Your line is now open.
Oh, hey. Thanks for doing this, by the way. This question is for Lindley Johnson. You mentioned, what else might be out there. So, we have all these exquisitely precise calculations and data on Bennu. How many asteroids the size of Bennu might be out there that we just don't even know about? Do you all have any estimates for that number?
Well, yes. We do models of the population of objects out there based on what we have found so far, and what the potential could be for similar sized objects out there. We update that population model on a fairly regular basis, about every 5 years, with what additionally has been found. Bennu being an object that's about a half a kilometer in size, our level of completeness with the population of objects that size based upon that model is about 50 to 60% complete. So we're pretty well up on that curve, but there is a way to go, and that's why missions like the NEO-SURVEYOR mission are important in that it will pretty fully complete that population that size objects, and even further down in size, down below 140 meters in size.
Okay, so can I just restate to make sure I got it? So you're saying that right now, researchers know of about half the population of asteroids in this size that are predicted to be out there, but this upcoming mission would basically find the rest of them?
Yeah, that's correct. I think it's more than half. I think it's closer to about 60%. If you want a precise number, I can get that for you.
Thanks very much.
Next question is from Marcia Dunn with AP. Your line is now open.
Yes, hi, thank you. Another question for Davide. We knew before OSIRIS-REx that it was most likely, if Earth did take a direct hit, it would carve out a big crater, but it wouldn't destroy life as we know it. Is that still your going in thinking? Do you have any new evidence to suggest that its impact would be softer, harder, worse, better than what was previously known? Thank you.
No, I would say the situation would pretty much be the same, because the assumptions about the size and the mass of Bennu were mostly accurate, and so the damage to the ground would not change. But we now know better, which pathways could actually lead to that. And it's important to remember it's a very small probability, so we shouldn't be too concerned about it.
How big of a crater might it cause hit? Do you know?
I think Lindley might want to address that. It really depends on the impact location. Lindley, do you want to say more about this?
Sure. Like Davide says, it depends on a number of factors, but you can usually, by rule of thumb, say the crater size is going to be, 10 to 20 times the size of the object. So a half-kilometer sized object is, going to create a crater that's at least 5 kilometers in diameter, and could be as much as 10 kilometers in diameter. But the area of devastation is going to be much broader than that, as much as 100 times the size of the crater. An object Bennu size impacting on the eastern seaboard states pretty much devastate things up and down the coast. Those are all rules of thumb, though. It really depends a lot on the precise circumstances of the object and the impact, its trajectory, angle of entry into the Earth's atmosphere, and all those kinds of things.
Thank you.
Next question is from Kenneth Chang with New York Times. Your line is now open.
Hi, thanks. This is for Lindley. You mentioned that I think you mentioned that 50 years would be plenty of time to divert Bennu, but you didn't know exactly what technologies would be available. But I guess given current technologies and what's known about Bennu as sort of a rubble pile, what would be the most promising way of getting it into a safe orbit or diverting it?
Well, again, Bennu, we really don't think we need to do anything about Bennu. an object of that size, a rubble pile, you know, our current technology, kinetic impactors say it certainly would take multiple kinetic impactors, you know, one after the other, and kind of a shoot, look, shoot kind of situation to divert Bennu a significant amount, you know, which certainly is feasible in a 50-year time frame. But again, there are you know, other developing technologies and techniques that might be used with periods of time like that. You know, the gravity tractor idea that we have, and other technologies that are being looked at, like ion beam deflection technique. Again, you know, 100 years from now, who knows what the technology is going to be. The good thing about
this is Dante. I'll just add to that. But so from my perspective as principal investigator, what I'm most proud of is the exquisite data set that we have collected about Bennu. And it's important to remember, before OSIRIS-REx and before Hayabusa 2, we had never seen one of these spinning top asteroids up close and personal. But now we have this very detailed model of the shape at, you know, centimeter scale resolution. We've imaged regions as fine as millimeters per pixel. We know the mass, the gravity fields. We've been able to estimate the density distribution. We've seen these particle ejection events. So this data set is going to be enormously valuable for all these technologies that Lindley was discussing, because you're going to be able to model them very precisely and evaluate the pros and cons of them. So as a contribution to the security mission of OSIRIS-REx, just producing the body of knowledge of Bennu is going to help Lindley and his colleagues think about and evaluate the merits and the concerns associated with each of the deflection technologies under consideration.
Hi, everyone. I just want to let you know we're coming up to 2 o'clock. We're going to stay on a couple more minutes, take 2 more questions or so. Just to let everybody know, for time's sake, we'll stay on. But otherwise, if we don't get to your question, please feel free to email me or my other colleagues. Our contact information is on the media advisory we sent out. Thanks.
Next question is from Alexandra Witze with Nature Magazine. Your line is now open.
Hi, thanks. I want to press with Davide a little bit more kind of this notion of what is applicable to other near-Earth asteroids. In particular, sort of this focus on spacecraft tracking data and how that allowed you to pinpoint its future trajectory is, of course, really specific just to Bennu. Did you, for instance, sort of actually observe the Yarkovsky effect in action at Bennu? And if so, what precisely did you learn from that observation that would be applicable to other asteroids?
Well, I think one general comment is that we have been able for the first time to test our models for an asteroid trajectory to levels really never tried before. And the results are valid in general. For every other asteroid, we can apply these models and be confident that they're extremely accurate. The other aspect of it, you said about being able to use tracking data. Well, if we go to other asteroids, we can always use the tracking data from the spacecraft and try to use that for improving the orbit. The Yarkovsky effect can sometimes be constrained, not as well as we did for Bennu. For other objects, just based on ground-based data, we can get kind of the average effect along the orbit, even though we don't get the fine details that we were able to use here. But I think that the most important thing is that OSIRIS-REx was really a calibration mission, because we had a bunch of data from the ground, and we did our best to come up with the best interpretation of those data. But getting there with a spacecraft told us exactly how much we could trust the modeling done based on the data collected from the ground. And it turns out that we had done a pretty good job. And so that's going to be a valuable lesson to be applied for other asteroids as well.
And then this is Dante, just a quick follow-on. In addition to the Yarkovsky effect, which we have a very strong detection for here, And I think it's important to recognize that it's not just the spacecraft data that enables it, but the fact that we started observing it in 1999 and did irregular apparitions. We observed it during a campaign in 2005, which was right when we had selected it as our target, even though we were still developing the proposal to NASA. And then again in 2011, and then you add the 2018 to 2021 data set, and you have over 20 years, and that's where the signal for the Yarkovsky effect really shows up strongly. And we've seen a similar effect called the YORP effect, which is an acronym that describes the names of 4 scientists who contributed to our understanding of it, where, like the Yarkovsky effect, there's momentum transfer due to the absorption of solar radiation and emission back of that energy as heat, but instead of changing the orbital velocity, it changes the rotation rate. And we have seen that Bennu is spinning faster as a result of this YORP effect, and we have observed that and have a direct detection of that phenomena as well. So we're gaining incredible understanding of the physics of this absorption of sunlight and re-emission of thermal radiation and how it changes the dynamical state of the asteroid overall. And as Davide said, that's going to allow us to apply this knowledge confidently to many, many other asteroids across the solar system.
Next question is from Megan McNeil with KOLD. Your line is now open.
If I could jump in for just a second, this is Lindley. Answer to the question about what's our level of completeness of half-kilometer size asteroids. It's actually 79% according to the model. So I was being conservative.
And Megan McNeil, your line is open.
Awesome. Yeah. Thanks, everyone, for doing this. I think it's kind of interesting that we're all talking about, like, oh, we're watching this. We are going to see this. Obviously, none of us are going to be here in 2135, at least. Personally, I hope I'm not. So how do we kind of continue this science forward and continue looking at these issues and looking at asteroids and tracking them and coming up with diversion techniques or, you know, things that we need to look at? How do y'all kind of push forward the education and the momentum to keep future scientists and children involved and participate in this?
Yeah, I'll take that because, as I mentioned in my opening remarks, one of the key objectives of the mission is training the next generation of scientists and engineers to enable an educated workforce and to excite young people all over the world. And one of the most gratifying parts of being the principal investigator is the well wishes that I've gotten from international and national people all over the globe. And we're very dedicated to that. Davide is a great example. Davide is going to have students that he's going to teach these methods to. We're going to have, obviously, all of the material that we've put into the scientific literature and our amazing data archive that's going into the planetary data system. And then for OSIRIS-REx, the gift that keeps on giving is that sample. So we will have those materials on Earth. They will be studied immediately and intensely as soon as they're at NASA's Johnson Space Center at the curation facility that we're building there. But they're going to be available for decades into the future. We're still looking at Apollo samples and learning amazing new things about the formation and evolution of the moon because we have the rocks that were collected by the Apollo astronauts, and our techniques and our laboratory capabilities have grown substantially since then. So we can ask questions people couldn't even think of in the 1960s and 1970s, and the OSIRIS-REx samples are going to enable that for future generations interested in asteroid science, to understand the origin of the solar system, asteroid resources for future solar system exploration, and of course for security for orbit determination and impact hazard assessment.
If I could add to that, because I just got a report from him today, so it's on the top of my mind. We in the Planetary Defense Coordination Office support a project called the International Asteroid Search Collaboration. And what it is a team that develops a program that is available to schools not only in the U.S. but around the world for providing materials for students to actually search for asteroids in images that are provided by our survey projects, so they can learn about what it takes to find asteroids in space measure their positions and provide that data to our minor planets and as a repository of all observations and orbits. So it is teaching the next generation of asteroid hunters.
Next question is from Michael Greshka with National Geographic. Your line is open.
Thank you. A question for Davide. There are some upcoming close approaches of Bennu, notably in 2037, that could provide a check of your orbital calculation. How, what are your thoughts on additional observations and also the importance of ongoing and future surveys of the solar system, including what the Rubin Observatory will be doing starting in a couple years? Thanks.
Well, so about Bennu and the possibility of new observations, I would say science is always about, coming up with models and comparing your models with data. So I just look forward to getting more data and comparing that to the orbital predictions that we made, and we're confident everything is going to line up just fine. But that's the purpose of getting data. We want to get more data and improve our knowledge, so we're going to keep doing that. In general, about the other surveys coming up, we also look forward to that because they're going to give us what we need in order to find more of these asteroids, increase essentially the census of the known objects, and that has serious scientific implications in our understanding about the formation of the solar system, but it also allows us to get a better idea of what asteroids out there could be a risk to the Earth.
Great, thank you.
All right. Thank you, everyone. That's all we have time for today. Thank you to the journalists who dial in and all the great questions. And I'd also like to thank the panelists and our operator for their time today. If you joined this telecon late, you can listen to the entire recording by dialing 1-888-566-0418. Again, that number is 1-888-566-0418. And you can also continue the conversation online about asteroids and planetary defense by going to hashtag AskNASA on Twitter. Thanks again.
Ouvimos então o podcast referente às novas atualizações sobre OSIRIS-REx. Continue nos assistindo. Por enquanto encerramos a nossa programação. Agradecemos a todos que estiveram presentes até o presente momento. E estaremos em breve para a próxima live, ainda hoje, com outras informações. Para você que não é inscrito no canal, por favor, se inscreva, deixe o seu like, comente, isso ajuda na relevância do canal. Mais uma vez, obrigado pela audiência, obrigado ao Cairo, obrigado a todos que futuramente assistirão esta live. Mais uma vez, muito obrigado a todos, tenham uma excelente tarde.